All right, everybody, let's get started for Code Astro Day 2. How's everybody feeling this morning? Pretty weak. Come on, how are you feeling? Yay! Slightly less weak. That was good. We'll work on it.
Most of us saw 5 years.
What'd you say?
Most of us saw 5 years this morning.
Oh, the deer, yeah. I saw deer this morning too. I saw like a mother deer with 2 baby deer right when I was walking in. That was pretty cute. Yeah. Okay, so day 2, we're going to do quick intro slides and then we'll jump right into Gitflow. So first, just want to remind you about the anonymous feedback form. You can fill this out as often as you want. A couple of you filled it out yesterday, which I really appreciated, and we were able to make some adjustments based on your feedback. Okay, we also just want to remind you about this pair programming paradigm, and remember that pair programming is going to be like kind of awkward and difficult for the first couple days that you do it. We really want to encourage you to push through that, especially today, and get used to the paradigm. So just as a reminder, in pair programming, one person's the driver who types code, one person's the navigator who watches what gets typed, offers directions. Driver thinks more about small picture stuff, having the right syntax. The navigator thinks more big picture about how the code should work or function. The key is to switch back and forth constantly so that everyone gets the chance to do both things. And you can use Discord or Zoom or Skype if it's 2017 to share screens. All right, also want to remind you about all the various ways that we have set up for you to ask questions. First of all, we want you to ask questions as often as possible. The more you ask questions, the more you'll get out of this workshop, the more we'll be able to tailor it to your needs. You can ask questions on Zoom in the chat box. You can use the raise hand tool or ask a question in the chat, and people will be monitoring this before, during, and after the lessons, so you'll get your questions answered in real time. On Piazza, you can also get questions answered in real time here. There's also an anonymous option on Piazza, which I really like. At the end of the day yesterday, I encouraged everybody to post a question on Piazza. If you haven't done that, I really encourage you to do that now, or make sure you do that by the end of the day today. And then you also have Discord. This is the way we're recommending that you communicate with fellow participants. If you have questions about logistics or anything like that, that's also the way to go. All right, so just also want to remind you about the overall goals for this workshop. By the end of the workshop, you'll be able to use the language of software development, develop and release an open source astronomy package, and write code that follows best practices of software development. And today specifically, the goals are to be able to reason about Git to understand how to use it to version control your code, to interactively debug code using breakpoints and not rely on print statements. And for your project, the project goal specifically for today is to get a feature working and committed to GitHub. I know this is really fast, but this is kind of the last day to work on the functionality of your package. You're going to be pretty busy later in the week doing documentation, testing, actual releasing of your code on PyPy. So try to get something you can demo today finished. So an example, going back to this GalPy example that I talked about on the first day, is that my group members and I will continue working on core functionality we sketched out yesterday, so that at the end of the day today we can produce a plot of likely galactic orbits giving a Gaia star ID. We've got 2 optional lessons this afternoon. One at 3 to 4 p.m. is parallel programming, so running the same code on multiple cores. And then at 4 to 5, we're going to talk about JAX, which is a modern sort of language for running code on trivially easily on GPUs, and it also has a lot of nice extra features. It's really popular in machine learning and also getting more popular in the Bayesian stats community. All right, the last thing is that before we get started, we want to make sure you have the latest version of Code Astro. So there's 2 different ways you can do this. This is also the same thing that I showed yesterday. The command line version of this is cding into the Code Astro directory wherever you have it. And then any changes that you made to the repository, you can sort of save with the git stash command. Then you want to pull the latest changes from GitHub down to your local computer. So git pull origin main. And then you can reapply the changes that you made. So git stash pop. I also want to show you how to do this with the VS Code user interface. And in general, in Gitflow, we're going to use the VS Code interface more than the command line today. Let me share my whole screen. All right. Okay, so here's the Code Astro repository. We go down here. You see down here in the bottom left, this is the thing that tells me which branch I'm on. So here it says that I'm on the main branch. We're also going to talk about Git branches later in this lesson if you're not familiar. So you want this to be on branch main. This 3 with the down arrow means that there are 3 commits on GitHub that I don't have on my local computer. And then this 0 up means that there are 0 changes on my computer that aren't synced with the GitHub version of the repository. So to sync everything, all I need to do is just press this button. It'll pull down those changes. It'll also push changes if I have changes locally that I want to put onto GitHub. And then that's it. If there are any merge conflicts, you'll also have to resolve those merge conflicts at this point. But if you run into any issues with this, you can ask a TA. All right. And then also just want to let you know that we're going to do a workshop photo both on Zoom and in person today at the end of synchronous activities. So we'll do the Zoom photo first. So if you feel comfortable, we'll ask you to put your video on, and we'll take a photo of everybody. And then the folks in person will all go outside and we'll take a nice photo. And Jason does some nice editing magic to put everybody in the same room together at the end. All right. Any questions before we get started, or should we go right into Gitflow? All right, cool. Yep.
Where's the anonymous feedback form?
Good question. The question was, where's the anonymous feedback form? So it's on the first slide here. If you go to the Code Astro GitHub, you can find it in lots of different places. One is if you go to day 2 and then scroll down to the day 2 slides. That'll be the intro slides here. Then you can just get to the anonymous feedback form on this first slide. I'm pretty sure it's also in the helpful links. Yeah, so this workshop info.markdown, the anonymous feedback form link is right here. Thanks, good question. All right, let's go into Gitflow. All right, so we're going to be talking about Gitflow. As Jason mentioned yesterday, Gitflow is a way of using Git and GitHub in order to basically just avoid merge conflicts as much as you can, to streamline the process of lots of people working on the same code together at the same time. So by the end of this lesson, you'll be able to describe the basic Git workflow. It's just called Gitflow. You'll be able to create multiple branches within a Git repository and also make a pull request from one branch into another. So the first thing I want to do is just remind everybody of some vocab words and definitions. So these are all mixed up. The first thing I want to do is give you 3 minutes to just on your own, in a notebook or on your computer, try to batch up the word to its definition, and then we'll do it together as a class. All right. Okay, so anybody want to let's go through these together now. Okay, so I'll just go through it actually. Well, no, let me ask you. So which one is Git? Which defines Git? Yep. 5, yep. A piece of software that defines, reads, and modifies repositories. Let's move that up there. What about GitHub? 6, yep. A website that stores repositories and also runs Git. What about source control? 1, yep. The practice of storing changes you've made to your code alongside the code itself. So you can also do source control with having a Word document saved as version 1 final, version 1 final, final, final. All right, what about repo? 2, yep. The current version of the code and documentation plus its history. What about commit? 4, yep. The smallest unit of a code's history, a set of changes At Google, these are called CLs, which is change lists, which I think actually kind of makes more sense to me. What about branch? A pointer to a version of the main code that diverges from the main line of development. Exactly. So last clone is to create a copy of a repository that you can edit on your computer. Nice. Okay. And just as a reminder too, we've got this vocab list here that you can also access from these slides. So if you run into any vocab words that you're not familiar with, please feel free to use that. Okay. So why do we need Gitflow? In general, hopefully you got some motivation for this yesterday when you were all working on the same repository and everybody had merge conflicts. In general, when you're working on a big project, lots of people are committing at once. Source control allows people to edit the same code base at the same time, and Gitflow, so source control allows you to do this. Gitflow is a way of using branches in order to organize this process as much as possible. So Gitflow is a way of using Git and GitHub. There are certain advantages of Gitflow, which I'll come back to after I describe what Gitflow actually looks like to you. So it allows for multi-user development and testing. It protects the main code and makes sure you can go back to a stable point if something breaks. And it also allows you to perform work in parallel on one or more feature branches. So lots of people can be working on things independently at the same time. Okay, so here's how it works. You start off with 2 branches, a main branch, and then the first thing you do is you create a develop branch. Main is going to be the one that's stable, that users will see. Develop is where you pull in multiple changes at once, and if there are merge conflicts or things break, develop is the place where you want that to happen so that the main branch stays protected and the users only see that. The next thing you do is if you want to make a change, you add a feature branch. You make a bunch of commits on that feature branch, and then you make a pull request, which is basically like asking the an interface for asking the main developer of the repository, which may be you, to pull these changes into the develop branch. You then take this feature, you merge it into the develop branch, and then once you have several changes that you're happy with, and you want to release a new main version of the code, you merge develop into the main branch again. And then from there, you have your new develop branch, and you can keep creating features and going this way. So just to remind you, now you hopefully can see that this allows for multi-user development and testing via feature branches all being worked on at the same time. The fact that all of the merging and conflicts and potential breaking of the code is happening on develop rather than main protects the main code. And the fact that it's easy to go back to a stable point if something breaks is you can see that from the fact that you've got these versions on main, so you can always go back to the previous version on main. And then you get to perform your work in parallel. You can make as many feature branches as you want. So the first thing I need to do to you is confess that I don't always follow Gitflow. And I'll tell you when I do and when I don't follow Gitflow. So I tend not to make a develop branch unless I expect a lot of changes to happen at once. So in certain cases when I did use a develop branch were just before releasing major new versions of a software package that I was working on. So if multiple users were working toward, multiple developers were working towards a goal together, and everybody was, working on lots of different features at the same time, I had a develop branch to make sure I didn't break anything in the main code. And also when working on industry code, if you're releasing it to lots and lots of people, it's pretty standard to have a develop and a main branch. Each developer will all follow their own flavor of Gitflow. So when you're working on a new repository, it's important to get a sense of what the expectations in that repository are. All right, so now I'm just going to show you how to actually do this in Git and GitHub. So in this demo, I'm going to show you how to raise an issue in a repository, create and manipulate multiple feature branches, main, develop, and feature, how to use these branches in the standard Git workflow, and submit a pull request on GitHub to merge 2 branches. All right, get my notes up. Okay, so the first thing I'm going to do is raise an issue in a repository. So let's go to the Code Astro GitHub. How's this text size? Is this big enough for everybody? A little bigger? How's that? Yes. Is it folks in the back? Can you see okay?
A little bit more.
A little bit more. Okay. How's that? Okay, cool. Thanks. Oops. All right, so the issues are up here. Issues, depending on the repository, can be kind of like a to-do list of things we want to change about the repository. And it's also a way for users to communicate with the developers. So if you find a bug or if you have a feature request, the main way to like communicate that is with through the issues. So we can raise an issue here. Let's say I'm tired. Please add more coffee to station in morning. Hopefully we don't actually need to do that. I think I got 5 gallons of coffee, which seems like a ridiculous amount of coffee to me. The other things you can do here are you can assign particular developers. So you can see people that have developed Code Astro in the past. You can define, you can label, you can assign. You can also label the issue as like a bug or documentation. This is something often that the developers themselves will do in order to like triage the issues as they come in. You can also like assign projects or milestones. So if you want to work towards a particular version of the code, you might want to label all the issues that you want to resolve before that version release. Okay, so let's create this issue. And now you can see when you go to the issues in Code Astro, we've got this I'm tired one. I will also so that was me as a user of Code Astro. Now me with the hat of a developer will respond to this comment. I'll say too bad, and then I'll close it. Thanks for the rocket reaction. That was very good. Okay. We're now going to create a new repository, and we're going to set up Gitflow from scratch there. So let's go to github.com. I'll go to my profile, repositories. Then I'll create a new repository. Matt didn't want to use the fun name, so I'll use a fun name. We can do cuddly fish stick. Love it. The best fried seafood ever. Okay. Can always count on Jason to laugh at me. All right, so we can choose whether we want it to be public or private. Another thing I want to briefly talk about here is a gitignore file. We're going to talk about readmes and licenses on the releasing code day, so I'm going to skip over them for now. A .gitignore file is a set of files or like patterns of files that are going to be ignored in your ignored by Git. This can be really helpful if, like, for example, you have really large data files that you don't want to actually like push to GitHub. You just want to keep them on your own computer, and you want to source control the like code that you're using to work on these files. There are standard gitignore templates. If you search for Python, I'll show you what it looks like when we actually make the repository. But you can also edit the gitignore file yourself, and basically any file name you add will automatically be ignored by Git. Yeah, I think that's all I want to say about that. All right, so let's create a repository. All right, so you can see we have one branch, only the main branch. So if we go down here, we only see main. So remember in Gitflow, we want to have a develop branch, and then we want to have multiple feature branches. So let's start by just creating our develop branch. We can do that by just typing in develop here. So we're going to create branch main. You can see it's up to date with main. That means there are no commits in main that aren't in develop, and vice versa. There are no commits in develop then there are no more commits in develop than there are in main. The other thing we want to do is once we have an idea for a feature that we want to create, we'll add feature 1. So let's create a new branch there. All right, so the next thing we're going to do is actually make some changes to feature 1 and create a pull request. I want to show you how to do this in VS Code. So let's, for the next part of this workflow, go back to VS Code. So open VS Code. I'm going to open a new window. Okay, you can see there's this option here to clone a Git repository. So we'll click on that. VS Code is hooked up to my GitHub, so if I clone from GitHub, it should automatically find recent repositories that I made on GitHub. So you can see we've got our best fried seafood here. So let's clone Cuddly Fish Stick. We're going to put it in the place where I put all my GitHub repositories, right next to my League of Legends save files. Don't believe me, I'm not cool. I don't actually play League of Legends that much. My partner plays it a lot more. Okay, so we've got our repository here. You can see our gitignore file. There's a lot of stuff here that it's going to ignore automatically. Let me also just show you how this works. So if I wanted to ignore anything called hello.txt, if I were to then create a file called hello.txt, you see how it's kind of like grayed out here. That means that Git's not tracking it. So if we go to the Git extension here, or not extension, what's it called, tab on VS Code, you can see it's also going to list all of the changes that have been made since the last commit. So you can see that gitignore has changed, but it doesn't show you those changes to hello.txt because those are in the gitignore. Let's now remove it from the gitignore, save it, and you can see now it's tracked here. All right, so let's now make some changes. We will say I had some coffee and now I feel happy. All right, so I'm doing everything that Matt did yesterday on the command line now within the VS Code user interface. This is how I actually do most things in Git. So much so that last year Matt wasn't here and I had to do the Git like demo, and I like totally messed it up because I never actually do it. We can first add the changes. So that's, remember, just communicating to Git that these are changes that we want to commit the next time we write commit. So all you do is this little plus button, and it's going to stage both of these changes. Another really nice thing about VS Code is that it'll show you differences between like the previous version of the code and the new version of the code. I'll show you that next. I'll make another commit with a change to hello.txt. And then we can make our commit message here. So let's say we added hello.txt. I'm going to undo these changes to gitignore. If you want to like undo changes, you can just do this little undo button. I'm going to discard the changes. So now gitignore is exactly the same as it was before. Then I'll commit those changes, and then, so those are now committed on my own version of Git on my computer. If I want to put them on GitHub, I'll have to sync the changes or push the changes there. So you can see in Cuddly Fish Stick, we still don't see this hello.txt up there. The next thing I want to do is, show you the interface when I make another change to hello.txt. So let's say I feel very happy. And then if we click on this, you can now see this is the old version, this is the new version. You can see it's pointing out to us that you added this very word, which is very nice. This is very helpful. Okay, very happy. All right, we'll add it, and then we'll commit it. And now we have two changes on our machine that have not been synced to GitHub. So you can see on the bottom here, there's 0 changes on GitHub that we don't have on our local machine, 0 commits, but we have 2 commits on the local machine that aren't on GitHub. So if we press this button here, we'll sync it to GitHub. And then if we refresh here, you can now see that, oh, sorry, I did it on main. Classic. Okay, well, now you can see that on main, we have those changes. Okay, let's quickly make an actual feature. This is maybe another good thing to show you, is that we can also, if there are changes on main which you want to pull into your actual branch, you do git merge main. So these are things that I do actually do from the terminal. Yeah, so the question was, this is a good opportunity to ask, what if you push to the wrong branch and what do you do? It really depends. A lot of repositories will have protections for certain branches. So like on Orbitize and on Code Astro, for example, like you all won't be able to push to main, for example. So those are also good things that you can set up for your own repositories so that you don't accidentally push to main. It depends. Like if you push to a branch that you really didn't want to push to, you can like revert the commit. So we're going to go over in the next lesson like what reverting commits actually looks like. So that's sort of like undoing the change. You could also just like rename the branch, or you could make a third branch, or there's all sorts of what's the painter guy, Bob Ross, like we don't make mistakes, we make happy accidents. Yeah, great question. Okay, so let's actually make changes. Let's first merge in these changes from main that we made to our feature branch. So I'm going to first get the feature branch that I made on GitHub and sync it to my local machine. So I'll go here, and you can see that it's detecting that there are 3 different branches on the origin on GitHub. So we're going to check out, or just basically sync this feature 1 branch. Now you can see on the bottom here, it says we're on feature 1. It's also crossed through these things here because those changes don't exist on this branch yet. If I want to pull those changes into this branch, say git merge main. All right. And so you can see now we're still on feature 1. There are 2 commits locally that don't exist on GitHub. Those commits have come from this main branch that we just merged in. So let's now make another change on feature 1 that we'll want to merge into develop. We can add something else to hello.txt. Let's say I don't know, I'm just happy about coffee, I guess. Very happy. Now we will add our changes. Added some more effusive praise for coffee. We'll commit our changes, and then we'll sync the changes to main. One other thing that I'll want to do at this point is now develop doesn't have those initial changes that I made to the main branch. So something else I might want to do here is pull in those changes from main to develop before we make this final pull request from feature 1 to develop. So let's now check out our develop branch, and we'll do the same thing, this git merge main. Now we've got our 2 commits here. I'll sync those changes to GitHub. All right, and now if I go back to feature 1, okay, I remembered to sync those, that's good. So if I go back to our cuddly fish stick repository, you can now see we've got main that has this hello.txt. We've got develop that also has hello.txt. This is also the commit message from the latest commit. And then we've also got feature 1. So you can see this one has an additional commit relative to develop and main. So now if we want to create a pull request, when you make changes to a branch, it'll pop up automatically here, but you can also just go to pull requests. You can do compare a new pull request. So this is the branch you're merging from. So you want to take changes from this branch and merge it into this branch. So in this case, we want to make our base branch we want to be develop, and our branch we're merging from will be feature 1. Okay, so there are a couple nice things you can see now on this pull request user interface. You can see something similar to the VS Code user interface where it shows you what changes were made between like this current branch and the branch you're trying to push into. You can see that there was 1 commit, there was 1 file change, 1 contributor. Let's now create a pull request. You can add some description of your pull request, and similar to when you're creating issues, you can add reviewers or assignees or labels, etc. So let's create our pull request. Okay, and now there's a bunch of nice things you can see. Similarly, you can see the whole list of commits. So if you have multiple commits in one pull request, which you generally do, you can see all of them. If you have any checks that will run automatically, which we'll talk about later in the week, like tests, those will show up here. And then any files that you change will show up here. You can also make comments on pull requests here, which is a really nice way for users and developers to communicate with each other. All right, so this is now ready for review. So the last thing we do is just merge this pull request. I'll confirm the merge. All right, so you're all set. The pull request has been successfully merged and closed. It's best practice, I know this sounds kind of weird the first time to say it, but to actually delete the branches after you are done with them. Remember, this is Git, so nothing's actually like deleted forever. You can always go back. It's still a part of the history, but you don't necessarily need this branch. It's fully up to date with the main branch, with the develop branch now. So we'll delete that branch. All right. So I think that's pretty much it. So the summary of the process is to first pull the latest code from develop or main branch. So that was what I sort of did accidentally at the beginning, was make sure that I had all the latest changes from main or develop. You then create your feature branch from the develop or main branch. You make your changes, stage, commit, and then push back to the feature branch. And then you submit your pull request on GitHub and merge your feature into develop/main. Then you repeat until enough features have been merged into develop, and eventually make a pull request from develop to main. And at that point, you might like release a new version of the code. All right, so let's spend 15 minutes doing these activities. So the two activities are, first, just making sure you can git pull the most recent version of the Code Astro repository. This is something I've been telling you to do at the beginning. I told you to do that yesterday at the beginning of the workshop and then today, but often it is hard and takes some time. So this is some dedicated time to work through any issues you're having with that. And then the next part of the activity is to make Gitflow, set up Gitflow for your project with your groups. So within your repository, if you don't have a repository for your project, create a repository for your project and put whatever code you have already there. Create a main branch, a develop branch, and at least 2 feature branches. Also raise an issue. Make sure you clone the repository to your machine. Make changes on each of the feature branches and open pull requests to merge them into develop. And then merge the changes. And then if you, if you want to see the demo again, I've got the link to the recording of last year's version of the Gitflow activity, so you can see that on YouTube down here. All right, so 15 minutes okay, or do you want to?
Sure.
Okay, figure it out. All right, so let's come back at 53 after the hour then.
Okay, everyone, let's get back started. I know you guys are making very good progress on Git, but let's continue that in the afternoon in your projects. We're gonna take a break. We're gonna still be talking about Git, but we're gonna take a break from actually typing on your computer. We're gonna think about how Git works under the hood, because I think maybe most of our experience with Git is here's a series of commands that someone told me to copy and paste into my terminal to run, and then that does something. But this series of commands is something akin to black magic, and that's how Git works. So today we're going to try to do a little bit, try to figure out what's happening under the hood of Git. And the idea of this lesson is to get you a little bit of intuition for Git, to maybe try to reason your way through things. Because we offer you a bunch of workflows to try to avoid issues with Git, but eventually you will run into issues with Git. Maybe you've already run into issues with Git. So this is trying to teach you a little bit about what's happening under the hood, to maybe try to reason through, what combination of merges and pulls and pushes and things like that do you need to do to get you back into a state that you want for your Git repository. So this is we're gonna do Git by hand. So this is like going back to physics 101. We're gonna write down our equations of motion and do everything line by line. We're gonna do Git line by line, like what happens under the hood. technically, we're actually not. This is not actually what happens exactly under the hood. But it's a very use. The actual implementation of Git is so it's unnecessarily complicated. So this is a useful abstraction for what's actually happening under the hood. So it's like a middle layer that's reasonable to think through without thinking about all the exact implementation details for how they literally program the Git. Okay, so we need to. Okay. All right, so let's start off with a git commit. This object, think of it like an object. So we talked about object-oriented programming, we talked about classes. Let's think of a git commit as an object. This circle represents a git commit. And this circle is an instance. It's an instance of a class. The class is the commit object, and this is one instance. And this class has a lot of things. It has an ID. The ID is a series of numbers and letters that's the name of the Git ID. It also has an attribute that's the parent ID. This is tells you like which Git commit did this commit spawn from. So that's the idea of its parent Git commits. It can also have an attribute that's like a list of all the changes that happened in this Git commit. So like we changed like this file input.py, we added text at line 0, we modified this file plot.py, we added text at line 12, and deleted text at line 36. It's like a list of all the changes that happened in this Git commit that you just made. And there's a message, you guys do git commit -m, you type a message, that also populates this attribute field for this git commit. And, it has all the things like the author name, the author email, and the time of the git commit as well. So this git commit is basically containing a quanta of changes that have been made compared to a previous git commit. It's kind of the atomic units of our model. We're not breaking anything to. You can't break a git commit to subcommits. This is the smallest quantity of change that we have in our git commit history. And a Git repo is basically chains of Git commits. So basically, a bunch of Git commits chained together creates a Git repo. Okay, so we have this Git commit attribute. Okay, so let's basically, write out by hand. We're doing Git by hand. We're no typing, right? I'm faking a terminal, and I'm faking in PowerPoint, I'm faking a terminal and making the Git commit tree. So let's pretend I'm making this is my code Astro package. I'm making a package that like turns those astronomical images that have different colors. It makes like a false color image and like plots it. That's my code Astro project. So if you are working on Git, but you're not actually using GitHub, you're just working with Git, you can turn any folder into a folder that's tracked by Git by typing Git init. So that makes this folder a folder that can be tracked by Git. So then, we like are actually coding. So we like type and add some code to this file called color.py to generate color images. So we make a bunch of edits. And just like how we have always been doing. And then we do git space add color.py, git space commit -m initial commit. And the terminal, our fake terminal has returned main 309f initial commit, one file's changed, create color.py. And that's what happens in our git commit tree. So this is our first commit in our git commit history. Its ID is 309f. Its parent ID is none because it uniquely is the first commit in the Git commit history, so it has no parent. The changes is that we've created this file color.py and we added text starting at line 0, and the message for this commit is initial commit, and then there's other metadata like who wrote this commit, the time of commit, and things like that. It's all in this Git commits. All right, so we made one commit. Let's say, we keep coding on this, and then we figure out that the red in the color in our plotting isn't being plotted correct, like isn't being done correctly. So we have a bug. We want to fix that. So we go type, and then after we fix that bug, we go git space add color.py again because we now made new changes to color.py. And then we do git commit -m fix red color bug, and then our little fake terminal says main 8A6C fix red color bug, one file is changed. So now our git commit history looks like this. We have originally our 309F, and now we have a second commit, 8A6C. 8A6C's ID is 8A6C. Its parent ID is 309F because it is basically a bunch of changes relative to 309F. So now, and its changes are, we modified color.py, we added text at line 12, we deleted text at line 36, and the message is we fixed red color bug. And notice in this particular instance, I'm drawing this arrow directed in one direction. Sometimes if you hear people describe it, it's called a directed acyclic graph. And what that means is there's a direction to the graph. You see, 8A6C knows about 309F. It knows that its parent is 309F. It knows that it spawned from 309F. So its changes are done relative to 309F. But 309F knows nothing about 8A6C. Remember, these were its attributes. Nothing about this do we know about its the child of 309F, right? 309F only knows about its changes and its parent, which doesn't exist. So this is why we draw these arrows, and this is why it's called a directed graph in Git, because only the commits only go in one direction. You can reconstruct the Git commit history by going backwards in time, but you can't do it forwards in time because the commits in the other direction. Commits don't know about commits after it, but commits know about all the commits happened before it. For simplicity, because I'll run out of space soon, I'm going to drop the arrows in the future. But keep this in mind that each commit only knows about its parent, but the parent doesn't know about its children. All right, so we can keep coding. So we want to actually now plot our images, because in addition to like producing that image, we want to be able to display it as part of our package. So we're going to go type, and we're going to write plot.py, which is going to module that displays our color images. So after we write that new file, we're going to do a git add plot.py, git commit -m added plotting, and then our little fake terminal says main 91E1 added plotting, one file's changed, create plot.py. So now we have a third commit, 91E1. Its parent is 8A6C, and its parent, which is 309F. So 91E1 knows about 8A6C. 8A6C again doesn't know about 91E1. And its changes is create.plot.py, and it has a message add plotting. So now we have a starting to make a git commit history, and you're seeing what each commit knows relative to other commits. Yes, question?
Why is the plot.py a child of the previous commit? In the previous commit, it only had a color.py. So there's sort of like two different files. So how is one of them a child of the other when they are two separate?
Yeah, so the question is how this commit only has plot.py, but like the other commits don't know anything about plot.py. How is one the child of the other? We're thinking about children in the sense of like it's maybe not the right name. It's like basically this is the list of changes that has happened, and this delta list of changes is done relative to this other commit. Does that make sense? So to get the full state of your current repo, you're basically going to add all the changes together. So you're currently at say 91E1. You could basically look at this whole tree. You start at 309F, it made some changes, and then you go to 8A6C, it made some changes, and then you go to 91E1, it made some changes, and that is now the current state of your observatory by adding all those changes together. That makes sense? Yeah, every commit is a series of changes upon the previous commit. And that's why the parent is important, because you need to know what you're making changes relative to. Right? Because you make changes relative to, like, say you edit, you can't edit color.py without it existing first, right? So if 8A6C was if 91E1 was the parent of 8A6C instead, that doesn't make sense, because you don't have color.py. How could you make edits to it? Okay. Now let's keep moving on to Git branches. So Git branches are basically pointers to where in the Git commit tree you are. Git branches are extremely light. I like to tell people branches are basically free. They are basically almost nothing in terms of storage. You can make as many branches as you want. They're just basically a list of pointers. Branches allow you to work on features in parallel, like we said, and our base branch is usually main. But Git branches it's nothing more than just pointing to where's the endpoint of this current branch. So we're currently on the main branch. Our main branch, basically, in addition to the git commit tree, we have a list of branches. And for each branch, we have the name of the branch, which is main. And then we have 91 and it has like what is the latest commit in that branch. So 91E1 is the latest commit in main. So to figure out what the whole branch what the whole main branch looks like, you basically start at the latest commit, which is 91E1. 91E1 knows about its parent, which is 8A6C. 8A6C knows about its parent, 309F. 309F has no parents, so you've gone and basically traversed the entire commit history. So we can basically, from just having a pointer that's to the latest commit in that branch, you can basically reconstruct with Git the full commit history, the full version history of that branch. Commits, like I said, not only do they not know about its children, they also don't know about which branch they're on. So one commit can be on multiple branches, right? Commits do not think or care about what branch they're on. They just know what changes were made in that commit and what changes and those changes were made relative to what other commit. That's all commits care about. So branches are kind of a layer on top of commits to basically, you can have multiple branches that all traverse the same commits to go back to the same history. Yeah, so you follow the arrows for the full branch history, and then there's also this there's also what's called a head pointer. You might see this lingo when you are like working with your Git repositories. Head pointer basically points to where you currently are right now. So currently we're on the main branch. So the head pointer is pointing to the main branch, which points to 91E1. So our current state of observatory is 91E1. So then we can reconstruct the full commit history, 91E1, 8A6C, 309F to get the full list of all changes that have ever been made to our Git repo. Okay, so the head pointer is just a special pointer telling you where we currently are at exactly. And then your branch is just a list of, for all your branches, what is the latest commit that belongs to that branch. This will maybe make more sense in a second. Okay, so let's say I want to make the plot interactive. So we want to make a new, so we can adjust like the colorings by eye. So we can want to make a new branch to work on this so we don't break the current branch. So we do a git branch plot upgrade and then do a git status, like Matt's favorite command. You'll see that we'll still return on branch main. So now you can see our list of branches. We have two branches, main, which points to 91E1, and plot upgrade, which points to 91E1. But our head pointer is pointing to main, which points to 91E1. So even though all these branches point to the same thing, they all have the same state. We're currently on the main branch because the head pointer tells us that we're pointing to the main branch. That's why git status tells us that we're on the main branch. But now we have two pointers, and those pointers can now point to different things if they wanted to. And one way to do that is, so next thing we can do to move to the new branch, you guys have probably run this command, git checkout plot upgrade. And then you do a git status now. We'll say we're on branch plot upgrade. The only difference that's happened is that the head pointer has switched from the main branch to the plot upgrade branch. That's all that has changed. The commits haven't changed. The pointers to the branch pointers haven't changed. It's just what is the head pointer has changed. Okay, so now we're on the plot upgrade branch. Let's now make more edits. We go type, and then we make some changes to both color.py and plot.py. So we add both of those. Git add both of those. We do a new git commit -interactive. Now we get our little fake terminal returns plot upgrade 353b interactive, 2 files changed. So now we have a new fourth commit 353b. Its parent is 91E1. And you can see that the main branch hasn't changed, right? The main branch still points to 91E1. It still looks the same. These commits never change, right? They still look the same. But now we have a new commit, 353b. I've purposely put it to the side here for stylistic purposes. Our plot upgrade branch points to 353b, and our head points to the plot upgrade, which points to 353b. So we're currently down there in the bottom right, and we can retrace the full commit history to get the current state of our files, which basically follows all 4 commits that we have in this repository. Yes, question? The statement is when I said that commits don't care about branches, but don't you also have to be mindful when you're on a branch and what commit you're making? This is true that we as the developer have to care about what branch we're on and where we're making the commit. I'm just saying we're basically pretending or thinking about putting our place or thinking if we were the commit, we have no knowledge of what branch we're on. You know, a commit just knows about what changes were made and those changes relative to what other commit. But we as a developer do care about these things. I'm just telling you, I'm just trying to break down the responsibilities of each of these portions of Git, basically, just trying to see, you know, what knows about what and what doesn't know about what, basically.
Think about it. When you're deciding which branch to commit to, you're deciding which is going to be the parent of this new commit. So the commit itself doesn't care which branch you're on, but you decide where to put it.
Good. Another question?
I have a quick question. So when you're going between branches, it just looks like you're not actually creating a new path, right?
Yeah.
It's just changing the pointer
Yes.
of the path. So you can still have a string, like even though it's linear, you don't have like splits, right? You're just changing the pointer of where you are.
Yes. Yes. The question
split up.
The question is when we're going between branches, we're just changing the pointers. We're not actually splitting up the code. That's right. We're in this kind of representation, we're just moving the pointers around. What's happening for you physically for your files is when you switch between, say, plot upgrade and main, right? The Git has to look at where main, if you go from plot upgrade back to main now, Git has to know, oh wait, let me look at main. Oh, main points to 91E1. So these are the series of changes. So let me basically go through the timeline, figure out all the changes again, and give you the state of the repository if I only add up the changes of 91E1, 886C, and 309F. So under the hood, it has to do some calculations. It's non-trivial, right, to change all your files back to the state. But in this representation, it's literally just moving things around. This representation is good for our brains to kind of think about how these things work. Okay, let's keep going. So now, maybe while we were in the middle of that, we realized that we had also have a bug on our main branch. Maybe we didn't color nan pixels correctly, so we should fix that. So what we can do is git checkout main. That'll move our head pointer back to main, which points to 91E1. So we do a git status. We'll be back on branch main. We go type. We add edits to color.py. We do a git add color.py, git commit -m fixed nans, and then we get main 9A329 fixed nans one file's changed. And now we have a fourth commit on the main branch as well. It's divergent now with the plot upgrade branch, and you can see that the main branch pointer now points to A329. The head points to main, which points to A329. And main has four commits, and you can trace them back to get the full commit history. And plot upgrade also has four commits, and you can trace that back to get its full commit history, but they're not the same anymore. All right, and then how do merges work? So we talked about git merges. Sarah demonstrated git merges. Pull requests are another way that creates a git merge. You merge one branch into the other. So let's say we've tested it and the interact plotting works. We want to merge these changes back to main. So how would we do this? We do a git checkout main to make sure we're back on the main branch. We do git status to confirm that. And then we do a git merge plot upgrade, and now we'll merge the plot upgrade branch to the main branch. If there are no conflicts, Git will automatically make this merge. And you'll see that you'll get a new commit 8443. 8443 is a merge commit, so it's a little bit special. It has not just one parent, but it has two parents. It's merging changes from 353B into A329. And that merge combination creates you a new commit, which is 8443, and it's special because it points to two parents instead of one. It has a bunch of changes as well. Those are the changes that are necessary to basically merge those two together. And the message is merge a branch plot upgrade. And so you can see that plot upgrade still has not changed at all. It still points to 353B. 353b still exists. If you check it out, it will still look like the exact same 4 commits, just like it used to look like. But now the main branch has an extra 5th commit. Main branch points to 8443, and the head points to main, which points to 8443. If there are no conflicts, Git makes this automatically and you get a merge commit. If there are conflicts, you'll get something like when you do a git merge plot upgrade, the terminal will output something like this, our least dreaded terminal output, most dreaded terminal output, conflict, merge conflict in color.py. So we have to manually fix these changes ourselves. So like, this requires pain and sometimes, trepidation to like type. And maybe we realize that, we added 2 different keywords and onto the same line of code, one on the head and one on the plot upgrade branch, one for interactive, one for mask and nans. And when we did that git merge plot upgrade, we get something like this, which Matt showed you yesterday. You get all these less than greater than signs, and he tells you that one of them looks like this, the other one looks like this, and you have to make a decision for how to merge them yourself. So we have to manually decide as humans how to merge them. Git doesn't know how to program; it just knows when things are different, and so we humans have to make those changes. So we go type, fix those changes, and then do a git add color.py to add our changes that we did to manually fix that conflict, and then do a git commit -m to merge branch plot upgrade. And now give us main 8443 merge branch plot upgrade, one file is changed. And in this example, in our kind of like git commit tree, this new 8443, it looks almost exactly identical to the case if there were no merge conflict. So for like all the hard work that we did to fix merge conflicts happens in the changes attribute of this git commit 8443. We did some hard work to modify color.py, including manual changes to fix those merge conflicts. But in this kind of like schematic representation that we're showing here, nothing is different from before, whether there were or weren't merge conflicts. Okay, so hopefully that gave you a little bit of intuition into Git. I think the best way to build intuition is to do it yourself. So your activity, let's see what time is it and how much time I have. Sorry, I have to check. Okay, so let's take the next 20 minutes. And I have 2 activities for y'all. So we're doing these without typing. So you can do this in like PowerPoint. You can do this on a piece of paper. But you don't need to do anything on the command line yourself. So let's say the first activity, let's say this is our git commit tree in 309F, 8816, 91E1, our favorite commits, commit IDs. This is the head pointers pointing to 91E1. Let's say that this is the current state of our branch. We run git pull to pull updates from remote, e.g. from GitHub. So this is what it currently looks like on our computer. Our computer has 3 commits, and we're doing a git pull to pull updates from GitHub. Draw out what happens to our local git commit tree in each of the following scenarios. The remote branch is ahead by an extra commit, 832E. And in the second scenario, the remote branch also only has 3 commits. But instead of 91E1, we have 832E. So it goes 309F, 886C, 832E on GitHub, which is different than the 3 commits we have locally. In these 2 cases, you guys now played around with doing some of this in the previous activities. You kind of know roughly what happens. Now that we've kind of shown you kind of this like mental model of Git, draw out what happens in the mental model of Git in these 2 scenarios. This is the first activity. Try to get this done for sure. Post your answers onto Piazza. There's a question for that. If you have time, you can also work on activity 2. Activity 2, someone asked about reverts. I'm gonna make you guys figure out what happens. So here are 2 ways to so basically, oops, I committed something wrong, and I don't want to commit in 91E1. I want to get rid of the changes in 91E1. These are 2 ways to revert commits. One is git revert 91E1, and the other one is git reset hard 886C. Look up what happens to them. Try making up a fake Git repo. See what happens in that fake Git repo, and try to make a git commit tree, draw out by hand what happens to the git commit tree in these two cases, and think about which of these commands you would rather use if you were to edit, trying to revert changes to your git commit history. You can assess when it's the right time to use these commands. Okay, so let's break for 20 minutes. So we'll come back at 45 minutes after the hour in your groups and post your answers to Piazza. I'll make sure we have two. We'll have one question for activity 1 and one question for activity 2. So post your answers. You can literally draw this in a piece of paper and take a screenshot of your phone and post it to Piazza. Okay, let's break now. Yeah, let's come back together. Let's see how folks did. So we asked folks to put things on Piazza. Hopefully some of you guys did. So our first activity was we had just remind folks, let's say this is the current state of our branch. We have a 309F, 886C, 91E1 locally. What would happen if the remote is ahead by extra commit 832E, or if the third commit instead of on remote, instead of 891E1 is 832E? So let's take a look at what. Yes. Yeah. So in this one, you can see for activity in the first activity for the first case when the remote branch is ahead by extra commit, you basically the origin is basically ahead by 1. So when you do a git pull, we're gonna basically pull that new commit 832E and move our head pointer over by 1, which you can also which you also see in and this very nice text representation. And then let's take a look at some of the other. Good. Here's a nice one. And in the second scenario, you'll see that in our branch locally, we have 309F, 8816, 91E1. But on you can think of GitHub or your remote as having a separate main branch. So you have a local main branch, and then GitHub has a remote main branch. So there's actually two main branches, even though they're both named main. There's a local main and a remote main. And the remote main went 309F, 886C, 832E. So we're basically, when we're doing a pull, we are trying to sync these two branches. So because they have differences, we had to do a new merge commit to basically produce, to basically get these two synced up. So now, after we did a git pull, our local copy basically has actually a branch, has a branch and a merge commit that merged that branch back, basically. So we recognized that there was a remote main branch and that looked different, and we had to make a merge commit to get both branches back and looking the same. Very nice. Good job. Let's see if folks have time to go to. Oh, very good. We see some nice ones here. So let's remind folks what this one looks like again. So here we have 309F, 8816, 91E1, and we want to get rid of the changes in 91E1 because we did something we didn't want there, and we want to totally get rid of those things. So we had two possible options that we found on the internet. One was git revert 91E1, and the other one was git reset -- hard 886C, or sometimes you see this as head tilde 1. Head tilde 1 means the one commit before head. So currently head is pointed at 91E1. So head tilde 1 means one commit before it. So we know 91E1 has a parent. So you go one parent up. So that goes to 886C. So in this case, doing git reset -- hard 886C is equivalent to doing git reset -- hard head tilde 1. If you sometimes see that, especially on Stack Overflow posts. All right, so in the first case, we do a git revert. What happens is kind of like this. Let's see. Yeah. Basically, this is a nice way to show it. We have 309F, 8816, 91E1. Git revert basically makes a new commit. That basically is like the antimatter to the matter that is 91E1. That basically the changes in this new commit is basically the exact opposite of the changes that happened in 91E1. So you basically git revert is basically making a new edit commit that just undoes the edits of the previous commit. A git reset -- hard is indeed in both of these cases, git reset dash dash hard literally moves the branch and head pointers back by one. So we've basically moved the branch and head pointers to 8A6C. So basically now the main branch is pointed to 8A6C and the head is pointing to the main branch, which points to 8A6C. And in this case, 91E1 is a commit that exists somewhere in your file system, but it still knows that its parent is 8A6C, but the Git kind of control history, the branches know nothing about 91E1 anymore because 8A6C doesn't know anything about its children, so it can't find 91E1. The branches aren't pointed to 91E1, it's pointed to 8A6C, and it can only go backwards in the Git commit history. So basically 91E1 has disappeared into the ether of your computer. And that's what git reset dash dash hard does. You could think about maybe in some cases where you don't want to do that, and maybe in some cases where you might want to do that. You want to put this thing into the ether. It just needs to disappear from forever history so we don't ever have it in a timeline. This often happens if you accidentally commit a 5 GB file to your git commit history. And you don't want a new commit that undoes that 5 GB file, because a commit that adds a 5 GB file, to undo it, you need another 5 GB commit to undo those changes, which maybe not something you want. So maybe you want to just completely get rid of that commit. It never needs you don't ever want to moving around in your commit history because it's 5 GB commit of edits that you don't want. Okay, one question.
Yeah, so when you say disappears, it actually disappears. So like if you accidentally put a password in there, nobody can see it.
The question is, does it actually disappear? Deleting things is actually very hard. So it's if you notice in your folder that's tracked by Git, there's a .git folder. Somewhere in there is that commit. So if you really want to get rid of it, you have to physically delete that file that's in that folder somewhere. I would not recommend trying to find that file in that folder. It is extremely complicated. But doing this to remote does make it so it's very, very difficult to find it on like the GitHub servers again. But again, when you commit something to the internet, you kind of lose a little bit of control over it, so you're never sure when it gets deleted, I would say. Yeah.
Can I? No,
Yeah, go ahead. No, you have.
Jump in with relevant personal example.
Uh-huh.
So I was working on a website. I was developing.
Maybe can you come up here? Yeah, so the Zoom folks can.
Yeah, so I was developing a website in undergrad, and there was like some sort of personal access token that we needed or something to enable authentication on a server, and I accidentally committed that, and it lived in a private repository for about a year. And once I realized that, I had to scrub that from the repository, and it was a bit of a pain. So like possible, yes, but that's like stuff like passwords and tokens and stuff. It's storing them elsewhere is good. So.
Yeah. There are ways to nuke specific commits, but it's good to have this kind of mental picture of what's happening in your Git commit tree to figure out how do I like precision nuke one commit out of existence and not the rest of my Git commit tree. Was there a question in the back over here? Yeah. Yeah. Yes. It's taking up 5 GB storage, say, on your computer somewhere, and you can probably try to go and hunt it down. But if you push this to GitHub and other people try to pull that GitHub repository, they don't have to pull that 5 GB file anymore. Yeah. Okay, one last question. We gotta move on.
Yeah. When you say revert does like the commit,
Yeah.
whatever, like if you revert to several steps, does it create just one commit to revert several things?
The question is, if you do git revert several steps, is it does it like have a bunch of steps all in one commit? And I forget, to be honest. It only does one. It only does one. Okay, that's.
So if you made a commit and then you made 6 more commits and then you revert only the first commit, your 5 future commits will still stay. Which kind of makes it confusing. You have to think about it literally like matter, antimatter. Like what were the things that you made in that commit, and it'll undo just those things.
Good to know.
Specify target to revert
The comment was you can specify a target to revert to. That's right. You can revert all the way back to a specific state. Yes. How to do that, the actual Git syntax, I don't remember, but the internet knows. But the thing is that this is the thing. This is the whole point of this exercise is we have this mental model, and you know now what's possible and what's not possible in a Git commit history. So then there's a bajillion Git commands, but you're like, I know I want to get to this state. How do I get the right Git commands to get to that state? Rather than just being like, my state is messed up. Internet, please help me. You have a very targeted focus now what you want to do rather than just being like everything is broken. I need to delete the repository and reclone it from scratch.
I Google Git syntax all the time. Like I don't remember like how to do the things, but having a model of what I'm looking for and what the command is actually going to do is very helpful. Intelligent Googling.
Yeah. Yeah, so that was the whole point of this exercise, is try to develop this kind of mental model in your head so you can try to reason and debug these things in the future. That's why all the activities were a bunch of edge cases for you, because that's where we want to use this mental model to kind of help you in the future. Okay, let's take a 9-minute break. We'll resume at 5 minutes after the hour, and we'll do debugging for the last lesson of today. So we're gonna wrap up today to talk about debugging. As promised, this is one of the things we think. Let's take a second to appreciate the vintage meme. I think this is some of my best work. Very good. Okay, so we're going to talk about debugging. Debugging, there's no magical silver bullet to debugging. There's not even like, here's a general process that will guarantee you success in debugging all the time. But we are going to show you some tools to help you with debugging, and then we'll end with some general philosophies at the end. Yes, okay. Yes, and the main tool we're going to show you is the VS Code debugging interface. This is one of the main reasons we are recommending you guys to learn IDEs and to learn VS Code. And this is also happens to be one of the hardest things to get set up in VS Code. So that's why we're going to do an activity. And part of the activity is just get this set up. Okay, so here I have some broken code in day 2. This is called debug matrix.py. This code is broken. It's supposed to generate random pixel art. But if I go to terminal, new terminal, is this text okay for everyone, by the way? Oh, good. Back? Okay, good. All right, so we go to day 2. And then I'm going to run debug matrix.py. And it's gonna crash. And you're like, oh great, it's crashed, it's broken, it's debug time. Okay. So this is where we're gonna show you a few things to kind of help you with this. This is all gonna be based off the VS Code debugger. Every IDE basically has some sort of debugging interface. The VS Code debugger on the left-hand side, if you come down to this 4th thing with this little bug, this is the run and debug feature. If you click on it, you probably don't have these settings. Let me just delete this. Save. Okay, okay, let's go back to debug matrix, sorry. You're gonna open it up and you're gonna see something like this. You don't have any sort of setting. In our README here, we have kind of we'll go through how to set up this debugger, but I'm gonna just go through it kind of right now without following those steps, but all the steps are written out in the activity that you're going to do in a bit. But first, I'm going to demo the features of the debugger. So notice I'm in the code Astro environment, and then I'm going to instead of just clicking run and debug, this big button is very tempting. I'm going to click create a launch.json file. This is going to create a debug environment for you. And you can do lots of different things, but I always just do a very boring one. It's just Python debugger, Python file. That's all I'm going to do. I just want to debug a Python file. There's just one thing I generally, this is just a bunch of configurations. I like to add one setting to this configuration, and it's called CWD : and I've added it so many times I have it memorized, and it's file dir name. What this does is that when you're debugging any file, it moves your current working directory. So like it CDs your terminal to the folder in which that file exists at. This is generally useful because sometimes you're in some random folder or you're somewhere you don't expect. this isn't on by default, but I like to do this thing. Like to set this so that I always know when I'm debugging. This is a JSON personal preference, but I like to go to set it so that I'm always in my working directory. My terminal is always CD'd to the folder in which that file exists in. And you don't have to memorize this. We have, in addition, in day 2, we have a demo launch.json here. So you can basically copy and paste, what's in here, and you can see it's exactly the same, almost. Is mostly the same. I think VS Code has evolved a little bit, but this current working directory thing remains the same. So after you set that in your .vs, you'll see that you have a launch.json. You can access it through this little gearbox button now. You click on run and debug. You have this little gearbox that you can edit your launch.json. And you have this, instead of this giant button, you have a run and debug with a little drop-down menu and you have now a single debug configuration, which is your Python debugger, debug current file. Can people read that? Python debugger, debug current file. And there's a little play button. So if I open up any file, so I'm going to open up that debug matrix file. This is the code that was broken before. This is a little too small. This is the code that was broken before. And I'm going to go into my run and debug setting. And I'm in the Python debugger current file. And I'm just going to hit play from here. And this will allow me to start debugging. And one of the things you'll see that it's going to run the code. And it's going to run the code until we crash. And this is called post-mortem. So you see it crashed right there. This is called post-mortem debugging. I really like post-mortem debugging. It basically stops your Python code at the line that crashes. And here you can see which line it crashed at. It has the exception for what happened. In the VS Code interface, there is a section called, can you get rid of this, please? Get rid of this, please. There's a section called variables. This gives you all the variables that currently exist in the current scope that you're looking at. So you have I is set to 0, J is set to 0, dim is set to 105, dim2 is set to 35. You have kind of the state of various variables. You can hover over things and it'll tell you the current value when it crashes. So I can hover over pixel RGB and it tells me that it's 0, numpy.float 0, 0.4. I can hover over image and it'll tell me that it's some sort of array. I can hover over J, it's 0. I can hover over dim and tell me it's 105. Dim2 is 35. Wait, sorry, I have a script I'm supposed to follow. This is a full disclosure, we had to fake some broken code, so I have to pretend that it's broken in ways that we were surprised by. Very good. We can hover around. Good. And then there's another thing called the debug console. So down here, you might have noticed you might have been using the terminal. We saw Sarah and Matt use the terminal for various Git commands. Next to it, there's this debug console, and the debug console is activated when you're in the run and debug mode. Here, it's basically a Python terminal that you can do whatever you want in. I can do 1 + 1, and it gives me 2. I can print out new image, J, I, and it'll give me a value, float 64. I can try things like, let's just set new image J + I equals to 1. And you'd be like, that works. You're like, oh, that's cool. That does work. I can try but why doesn't this equal to pixel RGB? You're like, oh, that creates an error. And then you can, you can basically type arbitrary Python commands here. So you can see that pixel RGB is some sort of tuple. It's not a single digit like what we expected before. So that's probably a source of the error. But you can basically type arbitrary commands in this debug console when you're stopped somewhere. Very nice. So this is called post-mortem debugging, and lets you basically look at the current state of your code when your code crashes. And you can try to investigate what's going on. This helps you solve kind of some of the bugs where things crashes. But in this case, you're like, so why is, obviously we don't want to set new image JI to a tuple. We want to set it to a single digit. Or in this case, why is this doing it this way? So So we can try to figure out how does pixel RGB get created. And we're going to do this just to demonstrate some new features. So you can see that pixel RGB gets created in the line before that. So we don't want to, we want to see what happens. How does pixel RGB get created? So maybe we don't want to stop the code when it crashes. We want to stop the code right before this line gets executed. So we can do something called breakpoints. So let's stop the debugger. And what we can do is we can set a breakpoint right here. So if you can see there's our lines of code, there's the little numbers for the lines of code, and to the left of it, there's these little these little red dots that can appear. You can click on one of them, and now I've set a breakpoint. What happens to a breakpoint is that the code will stop before executing that line. So it will, if you run it in debug mode, if you run it on the terminal, it'll do nothing. The terminal doesn't care about your breakpoints. But if you run it in the debugger will stop the execution of the script before it executes the line of your breakpoint. So here I'm going to hit run and debug again. You're going to rerun it from scratch, and you'll see that we've stopped the code right before we've executed this line. We stopped at the breakpoint we just manually specified. So here, I can go to the debug console and go like, what is pixel RGB? And it says pixel RGB is not defined because we haven't executed the line of code yet. So we can see that pixel RGB is generated by this function that takes j, which equals to 0, and I equals to 0. So what is this function? So we can, up here, there's another part. There's learning the IDE is sometimes a little annoying. You're like, why are all these buttons in all these various places? It's kind of hard to find. I agree. There's a lot of buttons and sometimes not very intuitive. But you have this little control panel up here. This is your control panel for your debugging activity. So one of these things, we'll go through some of what some of these buttons do. And I have to really hide this. Hide floating meeting controls. Okay. One of these buttons is called the step into button. A step into button, it will basically step into the line of script. So we're basically pause on this line. Step into will step into this function. So basically, once I click this, you'll see that we'll go into the generate pixel RGB function. We've set, x is equal to 0, y is equal to 0 because that's what was set when we called this function. On the left-hand side, there's a thing called the call stack. The call stack tells basically what things get executed. So we're basically we have stepped into this line of code, and this line of code has basically called another function. So basically, we've gone one level deep. Instead of just our main script, we've gone one level deep into a sub-function call. And you can see that actually the variables are different between the state of the main script and the state of the sub-function call, which only knows about x equals 0 and y equals 0. So inside the sub-function call, you can also keep stepping into things, but we probably don't want to step into numpy.random.uniform. That's like NumPy stuff, probably very complicated. So there's another thing called step over. Step over will execute that line of code and give you the next line of code. So it won't step into that function. It won't step into any function calls made in that line of code. It will fully execute that line of code and give you the next stop in the next line of code. So this will go to the next line of code like this, and you can do step over again. It'll execute the next line of code. You can do step over again. It'll execute the next line of code. And we can read this code and see that the generate RGB pixel function returns a tuple of red, green, and blue. So, that's probably pretty nice. We do want to return all three colors. And if I press step over again, I will leave this function and return back and fully execute that function. So now we know that pixel RGB is probably we actually want to set new image into as RGB. We want to set RG and B. We don't want to set one value. Turns out what we have to do is do this. I'm gonna skip some debugging. And so based on that, our understanding, we realized that we want to actually set RG and B. So we want to actually make new image into something like this. We can go back to our debug console and prove that this actually works. Let's remake new image, and then we can copy and paste this line of code. And now it doesn't crash. Great, it executes. You can see we have, and this actually produces some numbers. Great. We can now remove this breakpoint. We know we fixed this bug, and we can hit this restart button. This will restart the code from the very beginning, from complete scratch, without having, and it will re-execute the code again. And hopefully it runs. If it doesn't run, we'll stop again at postmortem. Oh, we crashed again in the same line of code. Doesn't work. What happened here? What's the script say? Okay, so we can now hover over I and J. So see, J is 0, I is 35. Seems like something is messed up here. Let's maybe just like test some code. So let's put our debugger back here, put this breakpoint back here. We're just gonna restart the debugger again. And I guess one thing I forgot to talk about is step out. Step out, if you step into a function and you realize, actually, I don't care about this function anymore, instead of running and clicking step over repeatedly until you finish that function, you can just click step out and it will fully execute that function and basically bring you back to your original, where you were previously. So I can keep going like step over and keep looping through the code and being like, what's going on? Why is it messed up? This takes forever. Sometimes you want to get to the right state. Okay, this is ridiculous, right? I can actually go to back to this breakpoint, right click on it and click edit breakpoint. With edit breakpoint, I can define a condition for which this breakpoint is set. Turns out the condition I want, I think, is J equals to 35, I think. So I can set a breakpoint for like, I only want you to stop when you hit this breakpoint. Otherwise, it will just pass through this breakpoint like it's transparent. So I hit enter, and then what I can do is instead of having to continuously do this over and over again, I can hit the continue button. The continue button will continue executing your script until it either crashes or hits a breakpoint that gets activated. So now I messed up the breakpoint. Okay, we're gonna do this again. I equals to 35. Okay, we're gonna restart. Okay, so now we stop the script exactly at when I equals to 35. You can see that J equals to 0, but I now equals to 35. And this is where it's going to crash probably. So we're going to go, oh, it crashes. Turns out, for the interest of time, I think what happens is we flipped I and J. So let's just flip it like this, and we're gonna just restart and just make sure it works. So again, we have the same breakpoint activated. It's gonna keep running until we hit I equals to 35, J equals to 0, and then we can go step over, and like now it works, right? It keeps going and it doesn't crash. So now we can remove this breakpoint, remove breakpoints, and hit continue to run. Oh, and it finished. Wait, where's our plot? Oh, it's because there's some issue with WSL, I think. Let's go back to our bash script. We gotta run this and get the plot. There we go. So we get our pixel art that gets randomly generated. And now we've debugged our script. So this was just kind of a contrived example just to show you some of the features of debugging, post-mortem debugging, breakpoints, stepping through line by line, stepping in, stepping out, the debug console, being able to run arbitrary commands to test things, and also having the call stack and the variables on the left to kind of monitor what state you're in. Okay, so I wanted you guys to kind of practice this and kind of figure out so this activity, we're gonna debug Orbitize. You guys, spent all this time installing Orbitize. Some of you went through some pain getting the test to pass. Part of it is that you can actually debug Orbitize. We have an issue for you to investigate. I was basically running this function in Orbitize called orbitize.kepler.calcorbit, and it was returning all nans. Do you know what's causing this? So here's, oftentimes it's always good when you're submitting a bug to submit a reproduction script. So that way makes the developer's life easy to basically reproduce your bug. So this is my reproduction script. You import NumPy, import Orbitize. You run this function with these very weirdly contrived inputs. And if you print out RA, DEC, and RV, you'll see that it's all nans. And you're like, what's producing all nans? So your goal, in this activity, well, first you need to install the development version of Orbitize if you haven't already. I think if you follow the install guide, you should have already done this. If you haven't, you just need to run these commands. Then set up the VS Code debugger. This is exactly what I just showed you at the very beginning, but here are like step-by-step instructions to hopefully do it all. So follow these. This is again list. This is you can find this in day 2, the debugging.markdown file. Then the goal is to basically follow this issue. Luckily, to kind of save you some time, we've reproduced this issue in this little script here. There's a script called broken orbitize.py. If you run the script, you'll see that it returns all nans, and this script will crash. Your goal is to basically put a breakpoint here and dive into Kepler.calc orbit and figure out what's going on. And in particular, we want you to report, and in the beginning, there's no nans. If you look here, there's no nans. Everything is a value. I want you to figure out what line of orbitize do nans first start appearing, and which of the 9 inputs that we arbitrarily called this Kepler.calc orbit function. You don't have to even care what this calc orbit function does. Is the one responsible for producing the NAN. So this is an example of you using the debugger to debug, say, a package that you're not really familiar with. This will encounter you'll run into this when you're like working with an unfamiliar package, but it's creating issues. What's the source of those issues? So this is an example of how you can use these tools to understand even a package that you maybe don't fully understand yourself. Let's take the next 20 minutes.
Sounds good.
We still have to wrap up, right? And the group photo.
We need the group photo, but I don't think we need to have that much work left.
Okay, let's take the next 24 minutes. So we'll come back at 50 minutes after the hour. So let's break out either on the Zoom and the breakout groups or break out into your project groups. Have one person be the driver, the other people be the navigators to get this set up. Maybe try to get it set up on only one person's computer first. And basically try to figure out this where are you first creating nans, and respond to the Piazza issue with what you find. And then we'll come together and do a little brief recap. So let's break out now. Okay. All right, let's wrap things up. So it sounds like a lot of successful debugger usages. I saw lots of people figuring out the issue. Let's take a look. So which line of the code? It was indeed basically a line 107 in this function. It starts returning nans because one of the values is negative. And indeed that value is the mtot argument, or the last one that was negative 99. And basically changing it to positive 99 will get you to stop producing nans. See, we got lots of that, line 105, mtot, line 107, mtot. Very good. So it seems like we got a lot of people successful as a debugger. If you are still running into issues, please post on Piazza or find one of the TAs, or we can help you try to get the debugger set up. It is a little bit of a pain, as some of you might have experienced the first time getting it to work, but with some effort, I feel like once I got it working, it saved me so much time in the long run, basically. I just want to end with a couple last points about debugging. There's basically no one recipe for debugging, but there's some general tips that you might find helpful. If you have no idea what's broken, try to first establish what's working. Try to establish what I call islands of sanity. A good process to debug when you have absolutely no idea what's broken. There's a bunch of lines of code. It's a method in programming called binary search. Basically, what you have is you have your code divided into the first half and second half. Comment out the second half and only run the first half. Is it still broken? Yes, no. If that part's still working, then take the second half, comment out half of the last half of the second at the last quarter. Is that code still working? If the first half was already broken, then take that first half, comment out that second quarter, and just run that first quarter of code. Is that still broken? This is binary search, basically dividing your code into halves each time to figure out where in the code is broken, trying to localize where that error is coming from. I actually do this when I have absolutely no idea what's causing the thing to be wrong. But with something like a debugger and postmortem debugging, I usually don't have to do this anymore, because usually I can just go to postmortem debugging and use the debugger stepping through its breakpoints, figuring out where the issues are. Googling error messages, using the internet as your friend in many of these cases. But the interactive debugger like VS Code helps a lot because, lots of these bugs are specific to your code and how you wrote things. And it's, having that context just really helps. One of the things to try to you can also use to debug your code is basically writing tests for your functions as you're writing the functions. So you can help them to debug your functions as you're developing them. So let's say you're writing a function that does something. Before you even write that function, write a test that's like, given these inputs, I expect this output, given call this function. That function currently is not written, so that test won't pass. But as you write that function more and more, and it gets developed more and more fleshed out, eventually that test will pass and will help you develop that test. This is called test-driven development, and it's a way that people develop functions and code sometimes to basically write the tests first before you even write your function. So we'll talk about testing more tomorrow. I think tomorrow. And lastly, you got to keep at it. You kind of develop an intuition for debugging the more you do it. Sometimes you might like see me passing through and I like help you with something and suddenly I was like, oh, you just have to change this line of code. Is it because I've seen that error like 50 times? The first 10 times were extremely painful, but after that, I've just like it's just ingrained into my head now, basically. And that, some of that just requires experience. So keep at it. Don't it's naturally painful for everyone.